confidence intervals for proportions. So proportions are probabilities themselves, and if they are percentiles, if they are percentages, then you just make them a fraction between 0 and 1 and use these formulas. So probability P of something, and you want to bound that probability, then you use this formula for the confidence interval. P plus minus plus Z 1 minus alpha by 2 is square root of P times 1 minus P upon N. Now notice that we have Z here and there is no T, because the probabilities cannot be normally distributed. Okay, and so they have binomial distribution, and therefore the thing is much more complicated if it is less than certain number of observations. But for more than 10 if the NP is greater than 10, such that what that means is that actually, to be correct, I should say that if NP and N times 1 minus P is greater than 10, so actually you at least have 10 observations which basically there are two possibilities, true or false, right? And if they say, let's say P is 0.99999, I mean that the other part, which is 0.001, you should have 10 observations. Okay, so valid only if NP or N times 1 minus P is greater than and N minus P greater than 10. This is an AND condition because both have to be greater than 10. Can I have a handout? I think today's handout. Yeah. So all right, everybody understands that condition 10, that you should, it's not just P, 1 minus P should also be such that N times 1 minus P is greater than 10. So you should have, if there are two possibilities, then you should have 10 observations at least of the lower possibility. And therefore if you want the one-sided confidence interval, then you start from 0 and go up to P plus, or you start from P minus something to and go all the way to 1. So the example is 10 out of 100, 10 of 1,000 pages. So the sample proportion is 10 upon 1,000, 0.01. Now notice that 0.01 times 1,000 is greater than 10. Actually it is probably exactly equal to 10. And so that's okay. So we go ahead with the formula, and Z value is for 90% confidence interval we use 0.95, and that is 1.645. For 95% confidence interval we use the other one. Okay, so now anyway, in this case we are using two-sided confidence interval. However, the way it is written is that the number of pages is 10 out of 1,000 pages. Right, so I mean it might be more appropriate to use one-sided confidence interval because you really don't care if the proportion is less. You just want to bound the upper bound on this. But this example uses only both sides. Second example is 40 repetitions on two systems. System A is superior in 26 repetitions, so the probability is 0.65, and 0.65 multiplied by 40 is 26, which is greater than 10. Now 0.35 multiplied by 40 is greater than 10, so formula is okay. And so then we go on to calculate the confidence interval as usual. And two-sided. And the interesting thing is that once you get the confidence interval, then you have to make a decision whether one system is better than the other. And that is same thing as saying that whether it is 50-50. Okay, and 0.5 is in the range, and therefore the systems are not different at this confidence interval. Okay. However, if you reduce the confidence interval to 90% from 99, then 0.5 is not included. So then you can say, well, they are different at 90%. And actually, you could also say something like they are different at 92% confidence or something, because you can just calculate where exactly this will be 0.5, hitting 0.5. You can go back to the G table and figure out that. And you can make that statement that at 90%, 92% confidence interval, they are different, but below that, they are not. So below that, they are different. Below 92%, they are different, but above 92%, they are not. All right, so now that we know how we calculate the confidence intervals, and then basically we can do the opposite, which is that we can calculate how many observations do we need to make a decision. All right, so if your mean is x bar, your confidence interval is x bar minus plus z times s upon square root of n. Now, if you want to be accuracy to be R%. What that means is that you want the answer to be correct up to that point. So R% is R upon 100 fraction. So basically, you want the answer to be in this range, and then you can calculate how many observations do you need to get into that range. N is equal to 100 times GS upon R x bar whole squared. And so with this, you can get the confidence interval as narrow as you want. So for example, if you wanted to say that I want that probability in the previous case, which is actually a different formula than this, but I want it to be in this range, and then you will know how many observations you need to get into that range. So sample mean is 20 seconds, standard deviation is 5. So how many repetitions are needed to get the response time accurate within 1 second at 95% confidence interval? So you want to be within 1 second. Okay. Basically, we are saying that we want to be between 19.5 and 20.5 at 90% confidence interval. So you put all those numbers there. R is equal to 5. Where did you get the 5%? Oh, 5% is R equal to R was R upon 100, right? Okay. So yeah, 0.05 in terms of fraction. And so you put all that and you get 96 observations you need. So 97 total observations you need. If you have 97 observations, so this is how you do simulations now. Basically, when we come to simulation, we will give you an even more complicated formula because of some other considerations. But right now, if you are doing simulation, simple simulation or simple measurement, and you did some little bit of what you call test cases, and if from the test cases you found out that this is the standard deviation, because to get that standard deviation 5, you have to do something, some number of observations. And so based upon those observations, you got these two numbers. Now you want to know whether, how much will you require to get within 1 second, and so that is the number. Okay, same thing, we can do the sample size for the proportions. If you want the proportions to be between P plus minus R, then all you do is equate these P plus minus R to P plus minus Z square root of P times 1 minus P divided by N, and you will get the value of N from that. So from the preliminary measurement, we found that the print rate is 1 in 10,000. So that is the range of P. How many pages must be observed to get an accuracy of 1 per million at 95% confidence interval? So this is P, 10 raised to minus 4. R is 1 in million, which is 10 raised to minus 6. And therefore, I mean, basically we put R and P and Z in the formula, and we get that we need 384 million pages to be printed. Any questions? Another example. An algorithm A loses 0.5%, algorithm B loses 0.6%. How many packets do we need to observe the state to state with 95% confidence that algorithm A is better? With 5% and 0.6%, actually, I mean, they look different, but the variance actually would be, we haven't calculated the variance, but we can calculate that by putting into the formula S. But right now, let's see how many observations we need. So the confidence interval for A is 0.005 from here, minus plus Z 1.96, which is 975 because of 95%, P times 1 minus P divided by N square root, and confidence interval for B is similarly 0.006 and all that. And we want to make sure that the two confidence intervals don't overlap, right? So the lower of this should be more than the higher of that, right? So to do that, basically 0.05 plus this thing should be less than 0.006 minus this thing. And if you do that, you will get N equal to 84,000 or 85,000. All right, so let us summarize what we have done so far. First is that everything that you are getting from the measurements are random quantities, or anything that you are getting from a sample actually doesn't have a measurement. It could be simulation. And you have just a sample, those are random and should be specified with a confidence interval. And so a mean alone is the first step, but really you should give some idea of the variance, and that comes out with the confidence interval. If the confidence interval includes 0, so that is one thing that at least I hope you learned new, is that now looking at the confidence interval, you can make some judgments. You can say whether this is 0, whether it is 0.5, whether it is 0.6. And if that number that you are looking for is included in the confidence interval, then basically you are saying yes, it is same as that number with that probability. Then we learned about paired observations and unpaired observations. Anybody remembers the difference between the two?
Paired observation has correspondence.
Yeah. So if there is one-to-one correspondence between the two sets of observations, those are paired. And with unpaired, there is no correspondence. So if there is a pair, then all you have to do is take the difference and take the zero mean, test for zero mean. If they are unpaired, then you have to do that new formula. And confidence interval apply to proportions too. And then you can do it for fractions as well. So now there is a homework here. And let me say this thing, you can do this homework, but you don't have to submit it. Why you don't have to submit it? Actually, you don't have to submit it 13A as well, because next Monday's exam. So I know you will have prepared for it anyway. So the purpose of the homework is to keep you, moving. So I don't need to do that for this week. All right, but let's look at the homework. For the code size data of 11.2, which was I think, if I remember, this was the simplified instruction set. What is it called? Complex CISC and RISC data. Find the 90% confidence interval for the average code sizes on the RISC and G8002. At what level of significance can you say that one is better than the other? So this is the opposite problem. We are not giving you 90 or 95%. We are asking you to figure out what percentage. So you calculate the Z value and then go and look up in the table and find the probability. How many workloads would you need to decide the superiority? So this is sample size. You have to compute n given that.